All right, let's get into it. Today, we are digging deep, literally, into the very first step of any huge construction project. We're talking about figuring out what's actually hiding beneath the surface. It's this whole invisible world that basically determines if a building will stand strong or not. So, let's explore it.
So, let me just ask you something right off the bat. When you look up at some massive, towering skyscraper, what do you think is the single most important part? Is it the steel, the shiny glass, the design?
Believe it or not, the real answer is the ground it stands on. I mean, any foundation engineer will tell you that. You simply cannot design a solid foundation unless you know exactly what kind of earth you're putting it on.
And that idea brings us right to our first section. You see, before a single blueprint gets the final stamp of approval, a whole different kind of exploration has to happen. You have to look down long before you can start building up. So what are they actually trying to do down there? Well, it really boils down to three main goals. First, you've got to map out all the underground layers. Second, you need to grab actual physical samples to test in a lab. And third, you have to run some tests right there, on site, deep in the ground. Let's talk about that first goal, mapping things out. What they're creating is something called a soil profile. And honestly, the best way to think about it is like a layer cake map of the Earth right under the building site. It shows you every single layer, or strata, how thick they are and in what order they appear. But here's the thing, right? The ground isn't always a neat and tidy layer cake. Sometimes you get a regular profile, where the layers are all nice and parallel, but other times you get an erratic profile, and it's just a chaotic jumble. Knowing which one you're dealing with, yeah, that's absolutely mission critical.
Okay, so how on earth do you create that map and get those samples? Well, it all starts with drilling. We have to literally drill down to get the data.
The go-to method for this is rotary drilling. You've got this big rig, and it's spinning a drill bit, just chewing its way into the ground. But here's where it gets really clever. As it's drilling, this special fluid, they call it drilling mud, is pumped down the drill rod. It shoots out of the bit and then flows back up to the surface, carrying all the ground-up bits of rock and soil with it.
And this drilling mud, man, it is literally the lifeblood of the whole operation. It's basically a slurry of bentonite clay, and it has two super important jobs. One, it keeps that drill bit from overheating as it's spinning like crazy. And two, it acts like an elevator, lifting all the excavated stuff, the cuttings, out of the hole. Okay, so the hole is drilled. Now comes the really cool part, getting the evidence. It's time to actually grab pieces of the earth from way down deep. And you can't just use one tool for everything. Nope. At certain depths, the crew will pause the drilling, pull out the drill bit, and swap it for a specialized sampler to go down and collect what they need. Now for soils, you've got two main players. First, there's the split spoon sampler. Think of this as a pretty rough scoop. They basically hammer it into the ground. It gets a sample, for sure, but the soil's natural structure gets totally wrecked. For more delicate stuff, like clay, they use a thin-walled tube, also called a Shelby tube. This is more like a very careful cookie cutter that gets pushed smoothly into the ground to keep the sample's structure intact for more sensitive lab tests. And this whole idea of a rough scoop brings up a super important concept, sample disturbance. It's all about how much you mess up the sample's natural structure while you're collecting it. And it's not just a vague idea, they actually measure it with something called the area ratio. Okay, get ready for this. A sample is considered highly disturbed if its area ratio is over 20%. So, what's the ratio for that standard split spoon sampler we just talked about? 112%. Yeah, you heard that right. That tells you just how much it messes up the soil, and it's exactly why you need that gentle Shelby tube for the really important tests. All right, soil is one thing, but what happens when you hit solid rock? For that, you need a whole different beast of a tool, the core barrel. This thing doesn't just smash the rock, it actually cuts and pulls out a perfect solid cylinder of it, which is called a core. The standard is a double tube version, where an outer barrel spins and does the cutting, while an inner one stays still to protect that precious rock sample inside. So you've got these amazing cylinders of rock up on the surface. But the job's not done yet. Now you have to play detective. You've got to analyze the evidence and give that rock a grade. And the go-to metric for this is the Rock Quality Designation, or RQD for short. You can just think of it as a report card for the rock. It's actually a pretty simple idea. You just take the rock core, look for all the solid, good quality pieces that are at least 10 centimeters long, add up their lengths, and then see what percentage that is of the total length you drilled. And this chart just makes it super clear, right? You get a number, and that number tells you the story. An RQD over 90%? That's excellent rock. Down below 25%? You're looking at very poor quality. It's just a really simple but powerful way to talk about how solid the rock really is.
Okay, cool. So we have a grade for the rock. But so what? Why does this number actually matter in the real world?
Well, it matters because everything we've talked about, the soil profile, the samples, that RQD grade, it all funnels directly into the final design of the building. It's all about making sure you're building on a foundation that is firm and, more importantly, fully understood.
So that RQD number isn't just a nice-to-have description. It's a hard-working piece of data. Engineers use it to estimate the rock's strength, to figure out how much it's going to compress under all that weight, and, crucially, to calculate how much load the foundation can safely handle. That's its bearing capacity.
You know, this quote just sums it all up perfectly. Without all this detailed investigation, trying to design a foundation would just be a wild guess. This whole process takes the guesswork out and replaces it with cold, hard data, which lets engineers design things that are smart, safe, and efficient.
So I'll leave you with this question. The next time you see a crane in the sky and a new building starts to rise up from the ground, will you maybe think about all that invisible work, all that science and investigation that had to happen first, deep down in the dark?